Polytechnique et l'EMINES School of Industrial Management. Et c'est ça qui nous donne le plaisir de vous avoir, intervenants, participants qui viennent de loin ou qui viennent juste du bâtiment à côté, organisateurs, exposants et autres pour ces 2 journées-là. Donc, moi, mon rôle s'arrête à peu près ici. J'ai fait mon travail pour les 2 jours. Je vais passer la parole tout de suite par capsule interposée à Hicham et Habti, le président de l'Université Mohamed VI Polytechnique, avant ensuite d'écouter le directeur général adjoint de l'École Centrale Casablanca pour les mots introductifs. Merci et très bonne journée à tous.
Professeurs, doctorants, étudiants, chers invités. Au nom de l'Université Mohamed VI Polytechnique, j'ai le grand plaisir d'inaugurer cette 2e édition des TechInnov Days à notre campus de Bengré. Un grand merci à nos confrères de Centrale Casablanca, notre cher Data Science et tous les collègues pour tous les efforts fournis en vue de notre rassemblement aujourd'hui. Je regrette de ne pas pouvoir être parmi vous aujourd'hui, mais en votre nom à tous, je souhaite chaleureusement la bienvenue à nos invités qui visitent le Maroc et l'Afrique pour la première fois. Je cite, en l'occurrence, Yann Lecun, lauréat du Turing Award, qui est aujourd'hui une inspiration pour les passionnés de mathématiques et de sciences des données. Si l'intelligence artificielle a réussi une chose de nos jours, c'est d'être pertinente à longueur d'année. Telle est la puissance de la 4e révolution industrielle qui vit notre planète depuis la démocratisation du digital. Mais même ce contexte-là de pertinence permanente, l'IA ne peut s'empêcher de nous surprendre à chaque fois avec des innovations qui promettent de révolutionner nos styles de vie et notre rapport à l'information. Petit exemple, qui d'entre nous ne s'est pas amusé à jouer avec l'outil ChatGPT ces 2 derniers mois? Loin de subir des disruptions dans l'économie du savoir, la communauté académique est bien positionnée pour les anticiper et même les modeler. Mais pas que la communauté académique, il s'agit d'une affaire de tous. Innovateurs, entrepreneurs, industriels et chercheurs ont tous intérêt à stimuler des synergies à cet égard. Les enjeux sont de taille. Propriété intellectuelle, ingénieurs des procédés, accès au contenu, modèle d'apprentissage. À l'UM6P, nous avons assez tôt développé une vision holistique du potentiel de l'intelligence artificielle dans le développement. D'une part, par rapport à un contexte africain en pleine émergence. Avec une pénétration du digital de plus de 43%, l'Afrique est un champ fertile pour l'implémentation de solutions en IA capables d'accélérer la croissance tout en prenant en considération les spécificités socio-culturelles du continent. D'autre part, par rapport à l'intersectionnalité de l'IA dans ses applications, que ce soit en santé, en agriculture, en éducation, nos programmes académiques accommodent déjà cette interdisciplinarité en impulsant l'intégration de l'IA dans l'élaboration de solutions. Je ne peux conclure cette ouverture sans inciter notre communauté UM6P à profiter pleinement de ces 2 journées pour échanger, élargir leurs perspectives et s'inspirer de la qualité des discours. Merci de votre attention.
Bonjour à toutes et à tous. Bienvenue à l'UM6P et merci à l'UM6P pour cette co-organisation. Bienvenue aussi avec mes remerciements aux conférenciers qui vont effectivement partager avec vous leur savoir et les développements à venir et les perspectives de l'IA au Maroc et en Afrique de manière générale durant ces 2 journées. Merci. Ils sont venus de loin, parfois pour la première fois effectivement au Maroc et en Afrique. Donc un grand merci à eux. Alors, je ne me suis pas présenté, je suis Adnane Boukamel, directeur général adjoint de l'École Centrale Casablanca. Je suis ravi de voir cette journée effectivement se concrétiser et concrétiser le partenariat qu'il y a entre nos 2 institutions depuis quelques années. L'échange entre chercheurs, c'est la germe vraiment d'une collaboration fructueuse, avec des résultats palpables. Et la preuve en est justement cette journée qui permettra non seulement le partage de la connaissance, mais aussi le lancement de projets communs, Inch'Allah. Alors, le sujet du jour, l'IA, je pense que Hicham a bien développé les enjeux justement pour l'IA pour l'Afrique. Effectivement, ça peut être un levier à la fois pour l'agriculture, pour la gestion des ressources hydriques, pour la mobilité, qui sont des sujets et des enjeux majeurs pour l'Afrique. Mais le point sur lequel je voudrais insister, même si Hicham l'a évoqué, c'est effectivement le partage et le développement de la connaissance. Je crois aujourd'hui qu'effectivement, l'intelligence artificielle peut être un vecteur majeur de partage et de démocratisation de la connaissance et du savoir. Et donc, par l'IA, on va pouvoir effectivement développer un vivier de compétences qui lui-même va pouvoir développer justement les activités IA pour les différents secteurs socio-économiques pour l'Afrique et pour le Maroc. Et donc, c'est un cercle vertueux qui va certainement pouvoir se développer en Afrique parce que, et pour une fois, justement, dans cette 4e révolution industrielle, on n'a pas besoin d'équipements lourds, on n'a pas besoin d'investissements lourds, on n'a besoin que de la matière grise et de la jeunesse, et ce sont des atouts pour l'Afrique. Voilà, j'en dirai pas plus. Un grand merci aux organisateurs et encore merci de votre participation et merci aux conférenciers.
Bonjour à tous, je suis Jean-Yves Dauxois, je suis professeur de mathématiques, de statistiques exactement, et je suis le chairman et je suis directeur des études de l'École Centrale de Casablanca. Et donc je suis assuré le rôle de chairman de cette conférence ce matin où nous aurons 4 conférenciers avec un beau programme. Nous allons commencer par Éric Moulines, et puis nous aurons la conférence de Yann Lecun, et après nous aurons Michael Valco et Reda Moula. Mais je vais d'abord commencer par la présentation d'Éric Moulines. Avant de présenter Éric, même s'il est évidemment très connu, je voudrais tout de même remercier tous ceux qui ont travaillé à la réalisation de ce beau projet. Je suis sûr que ça va bien se passer, tout est bien organisé. Donc il y a évidemment Nicolas, Cheimanoff, dont vous avez entendu tout à l'heure, ici à l'EMINES, l'École Polytechnique X, avec Éric Moulines et sa chaire et Marine Sow. À l'École de Casablanca, évidemment, Mohamed El Rabi, qui est à l'initiative et qui a fait un énorme travail avec toute une équipe autour de lui. Je nomme rapidement Jérémy Brabé, Adonajlo, mes collègues Adil, Khalid, Maha, et puis des élèves Kaoula, Herman, Abdelatif et Ayoub. Un grand merci pour votre travail, pour votre implication. J'espère que la liste est complète. Peut-être qu'il en manque, mais c'est celle que j'ai trouvée sur le site. Voilà, maintenant je vous présente rapidement Éric Moulines, qui est ingénieur et chercheur en mathématiques appliquées, diplômé de l'École Polytechnique que vous connaissez tous, et ensuite de Télécom Paris Tech. Il est professeur à l'École Polytechnique, affilié à l'UM6P ici aussi. Il a commencé ses travaux sur la recherche plutôt en traitement du signal, traitement statistique du signal, où il a considéré l'inférence de modèles à variables latentes, de chaînes de Markov cachées et des modèles d'état non linéaires. Entre autres, des résultats fondamentaux qu'on peut citer qu'il a obtenus sont sur le comportement en temps long des chaînes de Markov. Et puis, depuis quelques années, il s'est orienté vers des problèmes d'apprentissage statistique, notamment l'analyse des algorithmes d'optimisation stochastique. Il s'intéresse aussi à l'inférence bayésienne à partir de modèles à grande échelle, avec des applications dans un sujet important, évidemment, qui est la quantification de l'incertitude dans l'apprentissage statistique. Voilà. Merci d'accueillir Éric Moulines pour sa présentation.
Merci Jean-Yves. Donc, je vais commencer par quelques mots. D'abord, pour vous accueillir tous, vous remercier. Moi, je viens souvent à Ben Guérir, puisque comme Jean-Yves l'a dit, je suis donc professeur affilié à Ben Guérir et je suis responsable de l'option EMINES. J'espère que je ne vois pas encore les étudiants dans la salle, mais enfin, ils doivent être là. Oui, ils sont là. Bravo les étudiants. Donc d'habitude, c'est l'amphi où on fait la cérémonie de graduation. Donc l'amphi est bien plein aujourd'hui, c'est bien. Donc je vous encourage tous à... Bon, c'est des super étudiants, j'aime beaucoup enseigner ici. Des étudiants très dynamiques et c'est effectivement, ça reflète la dynamique d'un pays qui est le Maroc, qui a vraiment besoin, pour lequel je pense que l'IA est une chance, le numérique est une chance, que c'est effectivement, comme ça a été souligné, il n'y a pas ce problème qu'avec d'autres sciences où il y a besoin d'infrastructures, de très grosses infrastructures. Là, le numérique, c'est du cloud, c'est du stockage, et puis surtout, c'est des cerveaux, et les cerveaux, vous les avez. Donc, il n'y a pas de raison que ça ne marche pas. En plus, vous êtes motivé et vous avez un cadre de travail qui est absolument remarquable. Voilà. En plus, j'ai un lien très particulier avec le Maroc, puisque je ne connais pas beaucoup de personnes. Ma fille s'est installée au Maroc, il y a maintenant ça fera 10 ans en 2014. Elle s'est installée en 2014, donc voilà, je me sens en moins pour partie marocain. Donc je vais faire ma présentation en anglais. Enfin, bon, quand je parle anglais, comme je dis souvent, c'est une très bonne première leçon de français. Et puis je vais un petit peu abréger parce que comme ça je vais rattraper l'emploi du temps. Voilà. Okay, so switch to English. So what I will present today is about what is called intelligence in networks, and I will try to just very briefly say what we do in Federated Learning. And in a growing foundation of multi-agent decision-making. So it's a joint work with many colleagues. We have been awarded this year with a European Research Grant, a Synergy Grant with Christian Robert and Michael Jordan from Berkeley. So some of the ideas so we are trying to develop some joint work there, but I will more speak of what we did before. So what is the current AI? So current AI is mostly based on single agent. So it's like you think about intelligence, which is embodied in one very big agent, and this is the idea which has been there for quite a long time. Okay, so go back. So what is? Okay, so what is? Oops, sorry. So there is a lag. So what's needed to do something a little bit different? So what our objective in this work is to develop a mathematically grounded field that are large scale, data driven, and socio-technological systems, and all these systems will be based on networks. Decentralized algorithms, and so we'll also try to understand how intelligence will be embodied in these networks, and it's very important how humans will be in the loop. Okay, so I will mostly speak about federated learning today, so because the research perspective are very large, so I think federated learning is already something which is interesting, and there are several interesting applications. Okay, so what is the objective of federated learning? Federated learning is a setup in which a machine is trained while all the agents are keeping their data decentralized and private. So typically the idea is that you have a central server, okay, which is a central node, an orchestrator, and you have several agents which are willing to participate to a kind of it's a federation of agents, so which are collaborating to learn models. So why you need many agents? Because especially with deep learning, the size of the model are huge, and in order to do some inference, to learn this model, you need of course massive data. And so if you look at the last success of AI, the last success of AI are all based on a massive data set. So the GPT-3 and large language model are examples, but there are many examples in vision or text to generative model and things like that. So they are all based on huge data sets. So up to now, these data sets are centralized. So which means that if they are centralized, it means that you lose, so those who are providing the data are losing more or less the privacy of their data because they submit the data to a central orchestrator. So what Federated Learning is trying to do is that you are trying to learn this type of big data models, but with data which are kept by the agents. And there are in fact two types of settings which are quite different in terms of they all fall under the same umbrella of federated learning, but in fact in practice it's two very different settings. One setting is called cross-device. So in cross-device it means that you will have many devices, like it can be IoT, it can be camera, it can be smartphones, it can be computers, which are typically linked with a communication network, wireless network, or 5G, 6G, and so on, or more at the level of... and then you have the central orchestrator, and all these agents then in cross-device have a limited amount of data. They are they might be not able to participate at one given time point. They are not all available, and their ability to communicate is impaired because the communication network is not always good. So this is really the cross-device. Cross-device is tens of thousands of agents, but each agent has small data, and you have a lot of problems due to latency in networks, loss of connectivity and things like this. And the other scenario, which is called cross-silo, which is very different. So it's the same idea. So you keep your data private, but at the same time you have a small amount of agent which have in general good data, but they don't want to share data for privacy reasons. So that's one of the big application is linked with healthcare. So they work with hospitals. So there are many. We worked with a society in France called Ecole, which has developed this type of cross-silo application for medical data. So you have several hospitals. So they have patient data. Patient data are quite large, good quality, but you need to do some federation to learn, for example, a task like detecting cancer on images and things like this. But in that case, in cross-silo, what you have very good communication network, and all clients are available at a given time. So, but that basically fell onto the same area. What are the current challenges in federated learning? These challenges are quite interdisciplinary, and I think this is why they are very interesting for a researcher and an engineer, because they do not require just machine learning or AI, but also techniques which are based on used distributed computation. So, of course, in federated learning, you have a lot to do on distributed optimization. So, how you want to optimize a model, and with loss function which can be evaluated only locally by agents. So it's like you want to do an optimization of functions, but each agent has only a part of the function. So you have also you have to take into account asynchrony in computation. So it's a major issue. So because all agents doesn't have the same computing power, so you cannot wait, for example, that a slow agent is finishing a calculation because otherwise it will impair all the community. So which means that you have to deal with optimization with lagged with agents which are called stragglers, so which are slow. So a lot of things linked with network topologies, how you can communicate over network. So the second aspect is privacy. So it's very important to be able to learn with privacy. So in privacy, there are many different aspects in privacy. You have called epsilon differentially private arguments, where you have noise. You have problems which are linked with cryptography, so which are like secure multi-party computation, and also secure aggregation, differential privacy. So there are many aspects of that. And there are also applications, and as a telecommunication engineer, I like this aspect also. It's like about information theory, communication theory. You have to deal with compression because the models that you are training are extremely large, so you have sometimes billions of parameters which are not uncommon, so which means that it's very important to be able to compress this model, so which means that you have to quantize the weights, you have to look at the problem of being able to use, for example, vector quantization or tricky scalar quantization in order to reduce the size of the model. Of course, you have to do that in a very clever way. This is linked also with compressed sensing, sketching, so there are a lot of ideas coming from in this area. You have also one aspect which is linked with probabilistic machine learning and statistics, so because when you start to work with many agents, you have to deal with what is called statistical heterogeneity, because agents can be, for example, if you are handling a vision task, which are one of the main applications of FL right now, Federated Learning. If you do, okay, so we are trying to do a semantic annotation of image. You don't see the same image in Morocco and in France, so which means that you have many users in Morocco, many users in France. They don't see. They see, of course, we all have A's and we all see scenes, but some scenes are more frequent in Morocco than in France. And so that's statistical heterogeneity. So which means the data sets are not evenly, so compared to distributed optimizations, that means the data sets are not evenly given to all the nodes. So some agents are, for example, if you think about labels, so if it is a classification task, there are some tasks where some agents are many labels of one type, and the other agents have many labels for another object. And so which means when we try to trace this type of imbalance in data set causes problems that you need to take into account. So that's statistical heterogeneity, which needs to be addressed with very specific device. As was mentioned by Jean-Yves, uncertainty quantification is an issue, because I had 3 lives already, so I was a communication engineer and I was a statistician in the middle of my career, so I am particularly concerned by trying to quantify uncertainty, and it's very important in the application we are looking at, for example, in healthcare, so because in diagnosis it's very important to be able to quantize the type of errors, and so we are working hard in this direction. If I have time, I don't think I have much time, but if I have time I will explain a little bit how we do that. You have also personalization, so because now you have okay, so you are willing to train a big model for a population, but of course, like okay, a vision model, but you see only some specific data, so you can try to have a kind of model for yourself. So you need all the federation, because otherwise it's impossible to learn such big models. But you can perhaps try to make some local steps in order to improve the model for your own use. And this is called personalization. So you tune the model for your own use and your own data, and much more. Okay. And as I said, there are many exciting problems which are as the intersection of distributed computing and a lot of things in this direction. So I did a lot of stochastic optimization. It's really there are many things to be done in this direction. And for example, with asynchrony is very important. Asynchrony is very important in all machine learning today because of the size of the model, not only in federated learning. Privacy, so of course everyone is very concerned about the privacy of their data, so and there are many interesting scientific challenges over there. Of course machine learning, but we are more user of machine learning, so we are more users, so we use machine learning, we use architecture, and it's more like how to deploy this architecture in a distributed or federated context. And also some computational game theory, but I will not have time, I think, to go very far in this direction. Okay, so what are my research agenda? So it's federated learning is a very vivid community, many people involved all over the world working in this direction. The first steps have been done by people from Google, and but there is a large community, so it's quite recent. So the first paper appears in 2016. First application was 2017, so it's not like so it's like a very new science. So it's this is why also it's also very interesting and exciting. Many things to do, so many directions which opens almost every day. So this is, I will not cover everything, but this is more or less the research agenda I have covered in the last 3 years. So I did uncertainty quantification. So I started with Bayesian uncertainty quantification, and so that was this is what I will, if I have time, I think I will not have time, but I will cover very briefly. Then we are working at conformal predictions, which is, I think, much more promising than Bayesian uncertainty quantification. So we do a conformal prediction in a federated context. So it's a new work that we are trying to do, and I think that opens because if you know conformal prediction gives a kind of distribution-free guarantees for uncertainty in your decision. So you construct confidence set which are distribution-free and which can adapt to any classifier, and you do that with your calibration data. So of course, if you have many agents, for example, in cross-device settings, so which means each agent have very small fraction of the calibration data, so very few calibration data. So which means that it's if you are willing to do conformal prediction only with your local data, it's almost impossible. So you need to be able to develop a conformal prediction setting by trying to use with privacy constraint all the calibration data for all the users, and you need to do that in a federated context and also take into account privacy issues. So it's a new domain. So personalization. So we develop personalization methods. So we have several papers on that, and we have been inspired by methods which more or less come from rather old ideas, which is using a kind of latent representation of the weights. So we did also federated EM. So I worked a lot in my life on the EM algorithm because it's Eric Moulines, so it's like it's like by chance, I would say. But it's expectation maximization, which is very important algorithm, especially when you do for mixture models or for latent variable models. So we extended EM in the federated context. And also and the last step, so this is something I done very recently, so it's about compression. So we have developed new compressors in federated context based on vector quantization. So it's block vector quantization, but with a very interesting mechanism that makes vector quantization unbiased at almost no cost. And this is very interesting because it's not linked with an optimization problem, is linked with so you can do that very cheaply, and more recently the impact of low precision arithmetic. So I worked a lot on trying to do net, for example, deep net, which works with very low precision, like 4 bits and for the weights, 4 bits for the activation. So there is because the models are huge. As I said, billions, 10 billions, more than that sometimes. So you need really to represent a model with very small precision in order to compress size and also to make it much more efficient. It is very important if you are willing to do inference, for example, in devices. And so this is why, in fact, there is all these aspects which are very important. Okay, so very quick spotlight because I have only 5 minutes. So I will stay on this presentation. So I will stay on this presentation. I will not switch because otherwise it will be much too long. So what is uncertainty quantification? So right now something which is missing in machine learning is a fair representation of uncertainty. So which makes that, and in fact the situation had completely changed in the sense that compared to what we were able to do before, so something, in fact in the last decade, many tasks are solved with extremely good accuracy, but the calibration is very bad. So which means that what happened is that you can have If you look at classification task, what you will, it has been observed, not only by us, but by many, that you look at the machine, you look at you just classify your images, and you look at the probability of an image. So you have the softmax at the end of your deep net, and you look at the softmax, and you look, oh, he recognizes something with a very, very high probability, like, and in fact, it is completely wrong. So, okay, so which means that you cannot trust. So the accuracy can be very, very high, but at the same time, you cannot trust that the probability. We always believe it. In general, it's when you look at the probability at the output of the network, the probability always almost 1 and 0, 0, 0, 0. So it's very, it's very much like that. So which means that he has not. So you cannot look at the probabilities that you obtain with your softmax as a kind of probability of this image. Okay, so which means that the calibration is very, very poor. And this has been observed. So in the classical setting of which is used for inference, which is a parametric setting. So here it's not federated there. So it's like you maximize a loss function, which is that you can interpret as a likelihood. You add eventually some penalty term. You obtain 1 point, and this point gives you a prediction function, and the prediction function, the predictive distribution, leads to overconfident estimation. So a method which has been there for quite a while to do uncertainty quantification is to use Bayesian neural network. So it was funny because the idea of mixing Bayesian inference with neural network is extremely old. It can be traces back almost to the first work on deep net. So I think at the beginning of the deep nets, the neural nets are from the end of 80s, and you can find traces of neural nets with Bayesian inference as soon as the early 90s, with especially a work by Radford Neal, which was very, very active. And in fact, until the 2000, I think one of the most successful predictor, which the implementation of neural net was the neural net, a shallow neural net, which was coupled with Hamiltonian sampling, and in the work of Radford Neal, so which was very, very powerful. So what is the idea on in Bayesian neural network? In the Bayesian neural network, instead of you assume basically that the weights, synaptic weight and bias come from some distribution. So typically you have a prior distribution, P of theta. Okay, so there are many. Typically people take isotropic Gaussian, but it's not necessarily a very good idea. And what you are willing to, that's the first part. So you have a prior distribution of parameters, and you have likelihood function. So basically, likelihood function is a product of exponential of the loss. So no big challenge there. So in general, the problem, there is a computational challenge because the number of data is very, very, very large. And what you are willing to obtain is a posterior distribution of the weight. So posterior distribution of the weight are more or less proportional to the product of prior and the posterior distribution of the likelihood of the data. So seems to be so at least at this on the surface it's a rather easy trick. And when you have this, what you do is that you can compute the predictive distribution. So now if you take a fresh observation, you can compute the posterior predictive distribution, which is where you have to integrate the prediction, which is provided by your model, that you integrate with respect to the posterior. Okay, well, of course, it's a bit more complicated than that because you are in very large dimension. So of course, the integral that you compute is over extremely large dimension. The data itself are extremely large, so there are a lot of computational problems linked with this implementation, to implement this idea. So what are the Bayesian inference in AI promises? So it promises to improve prediction, okay? So that there is a theorem saying that the Bayesian estimate is better than anyone else, okay? So you have reliable, normally between quotes, reliable uncertainty estimate. Of course, it's reliable up to prior distribution. So it's the use of prior, and the prior, of course, has a strong effect on this on the uncertainty estimate that you obtain. And it gives you, but I think for network it's a bit, it's useless because the size of the model are so huge that it gives you in principle a principal way to make model comparison. And of course, Bayesian approach naturally support active learning, continual learning, and decision making under uncertainty. So Bayesian deep learning community is very active. So as yesterday, I think when you take Bayesian deep learning, it's like something to 10 to the power of 5 results. So it's much less than other topics, but it's still, so it means that you have, and you have many applications, so which range from astrophysics to click-through rate prediction, fluid dynamics. So there are many applications of Bayesian DeepNet. Okay, so in fact, what you do when you do, so of course you have this big integral. So when you have this big integral, of course it's not you don't implement a big integral like that. So typically what you do is that you will obtain method to sample, and this is the idea of Bayesian model average. So what you do is that of course you will not integrate over very large dimensional space. So the idea is to, instead of relying on a single value of the parameter theta, you will try to sample sensible value from the posterior distribution or some approximation of the posterior distribution. And instead of having one prediction, you will combine several predictions. This is really what the way you have to interpret Bayesian model average. So instead of relying on a single predictor, you take into account uncertainty on the parameters by having not only one parameter, but several parameters which are generated in sensible manner, also between quotes, and you just aggregate the prediction in order to obtain the final prediction. So you have Bayesian gives you a way, it's a principal way to compute this predictor, but of course you have other ways like deep ensembles, SWAG, or even what is called Monte Carlo dropout, which is used many times. Of course, what makes Bayesian model averaging very challenging, there are many aspects. So it's very high dimensional, as I say, billions, okay? The posterior are very demanding, so there is multimodality, so there are some things that need to be discussed because in such large dimensions, so we are, I think it's fascinating in the sense we are extremely far from what we know in Bayesian statistics. So when you go to the neural network and deep nets completely change the nature of inference. Okay, so it's completely different. So it's and when you go to Bayesian, of course, all what you know on Bayesian statistics, like all this Bayesian consistency, or the fact that the prior are washed out when the number of data becomes large, or it's not true because basically there is no Bernstein von Mises principle for in Bayesian statistics for applied to neural net. So I think it's very interesting because, for example, the influence of prior does not vanish at infinity. So and there is so the prior keep a strong influence on the way you generate uncertainty. Okay, so which means that there are many unresolved questions in BMA. Okay, there are also other solutions. So of course there are other solutions. One which are quite used, which are variational procedures, which provide simple but biased approximation. So it is not that variational approximation are often not mode dropping, so you have problems to represent multimodal distribution because typically your variational posterior is not very complex. You can have deep ensemble, but a deep ensemble does not have a natural Bayesian interpretation. So deep ensemble is more linked with problems which has been addressed by people looking at what they call it's like in deep ensemble where you start from different initialization and you run your Bayesian neural network from different initialization and then you combine the prediction that you obtain at the end eventually with some weights. Okay, you can improve a little bit this, and this work was been done by Achille, who is there, so you know, so you can upload Achille, so Achille. because he was second last year and very close to the first, and at the Neurip's competition on evaluating approximate Bayesian inference in deep learning. And the funny thing is that so it was Gordon, so Neil Gordon who proposed the thing. So we did a massive. So they use a massive computation on ImageNet, and in fact you can retrieve in fact with techniques which are not Bayesian at all. So what Gilles did was not really Bayesian. It was something like multi-swag, so like Gaussian approximation, but using stochastic gradient descent only, so no Bayesian interpretation. And nevertheless, he was able to reproduce some of the aspects which have been obtained by using massive Hamiltonian Monte Carlo method on deep nets. Okay, so I will not have time to go through all these very nice slides. Okay. Because I have 5 minutes to go, 1 minute to go. So okay, so you will, if you are interested, you might ask. And just to conclude, just some perspective to conclude this what was presented. So now what are the next steps? So first, federated learning, uncertainty quantification, all the agendas that I have presented is far from being completed, of course. But there are other aspects I'm willing to develop, and if you are interested by PhD, so I think there are very, very much things to do there. So which is to go beyond federated learning, okay, and the idea to go beyond federated learning is to look at agents as being active and strategic, and this idea comes from. So there are many ideas which now in federated learning people start to look at this type of aspect. So there are many issues like which are I will not list all these issues, but incentive mechanism. So what is the incentive to participate to federation? Okay, you are an hospital, you have very good data. You are another hospital which doesn't have good data. So how do I rate? How do I incentivize the hospital which has very good data with respect to an hospital which do not provide good data, and which at the end of the day will obtain the same predictive model? Okay, so you need to have some kind of incentive mechanism, because otherwise you will have free rider people which we are willing to enter a federation of learning, but without providing data. You also have to, for example, you can consider privacy and fairness as economic goods. So this is also important. So when you add privacy on the top of a machine learning algorithm, of course you degrade performance because you will add noise on gradients. You add computation because you are looking at, for example, secure multi-party computation, or so which means that you have to implement cryptographic algorithm. So of course this has a cost, and also a cost because if you are willing to implement differential privacy, typically you have to add some fake noise. So you add noise on your data, so you add some disturbance of your data, which makes learning more difficult. And but you can trade that. So if you are ready to say, okay, so privacy is important, but if I have a little bit less privacy guarantee, nevertheless it's okay. So it's a privacy is economic good. You have also what you call mechanism design. So there are many aspects there where you can have all this trading are linked with aspect of data economy and mechanism design. So we don't have time to cover that, but I think there are many interesting issues there. Okay, and that's my just to conclude. This is a summary. So what I will go in the future, so with optimization, equilibrium, dynamical system, and Bayesian inference and sampling, which are my core. In pink, it was my core knowledge, and the type of application I'm willing to look at, like federated learning, learning with privacy, developing incentive, contract, and information, also. Reinforcement learning ideas, of course, in this context. So there are a lot of Bayesian ideas right now in RL. So I'm not sure that Misha Walkovic is there, who is there, will perhaps speak about that. So you can also do reinforcement learning in a federated way. So I think it's something I'm willing to develop also, and also some online matching. That's something else. Okay. So I think there are many very interesting issues there to lay out the mathematical foundation of a new field, which is based on decision-focused data science for decentralized strategic agents, where agents have heterogeneous goals, who are owners of their own local data, which can be valued and traded for services, which learn effective, timely action via management of exploration trade-offs, and which may be also collaborative or competitive. So I think I still have 10 years in research, and I think it's an agenda which will cover very largely these last 10 years. So thanks for your attention. Question? No questions. Good, so you can applaud me again.
Is there questions or comments? We have 5 minutes for that. Thank you for your talk, Eric.
So
No?
It's will be a bit vexing to have no questions. Achille, you can ask me a question, perhaps. No.
So maybe I have one question. You are mentioning privacy as a problem in AI. And what about, you mentioned at the end, fairness of the algorithms. I was asking myself if the Bayesian approach is a good way to take into account this fairness problem for
fairness. No, I think fairness. I'm not an expert, by the way. So I mentioned. So it's something I have in mind. You know. So is there a Bayesian way to look at fairness? So first, I'm not sure that the Bayesian. So I'm not sure that the Bayesian aspect. So now that I worked a lot on this Bayesian aspect for neural nets. Okay, and I think it's very interesting. And at the same time, I believe that it's a bit hopeless right now. Okay, and we need to go. It's a bit hopeless because the size of the model is constantly increasing, and because the size of the model is constantly increasing, you are in situations where deep nets are more or less interpolating data, and nevertheless they can generalize. So it's like, okay, so you are in a situation which is like a bit the contrary of when you open a book 10 years ago, everything was about, okay, a curve, okay, so you start to overfit, so immediately you stop, and people, you use KNN, so you use a single, a single network, a single neighbor, and it's very, very bad because you interpolate data, but you don't generalize. And so the problem there is that the number of parameters become huge compared to even the number of data. So which means that what happens, the phenomenon that you see is that priors are not, the priors play a key role, in fact, in certainty. So because, in fact, the data are not the posterior distribution, so you drop too much entropy in the weights, if you wish, in order that the posterior distribution can drive you to interesting decisions. So this is why people do a lot of tricks, even when they pretend to be Bayesian in Bayesian neural nets. So they use what they call temperature scaling. So they scale the temperatures, they call prior. So which means like you increase the size of the posterior, you increase the size of the likelihood with respect to the prior. And okay, so I think there is something which is fundamentally need to be understood. Okay, and I think it's perhaps using I think statistical physics idea. So I have no real clue right now. But when I enter the field, because what was my story? So you give me a CV. So I was doing speech processing when I was very young. For almost 10 years, I would say. Then I went to telecom, so I did signal processing and then statistics for about 20 years. And when I went to Ecole Polytechnique in 2014, so nobody was willing to do statistics anymore. Everybody was doing machine learning. So I said, okay, I need to go back to, and it was okay because it was time. The time were ripe to do a change. So I moved back to machine learning. And when you look back, you try the tool that you know, of course, because I knew Bayesian statistics, and they say, okay, so let us try that for neural net. But okay, I'm not sure that the most It's very interesting, so it opens a very, very interesting question. I think there are, of course, privacy machine learning is something important. I'm not sure that Bayesian neural network is a good idea, so, but as I think it opens tons of very interesting questions, but so if I would attack fairness problem, to answer your question, this is not perhaps the way to go, but...
Okay, last question, if any. No, thank you. So thank you very much again.
Okay,
Eric.
thank you.
So, maintenant, nous allons passer au deuxième orateur. Donc, j'ai le plaisir de vous présenter Yann Lecun, mais vous le connaissez tous. Il est considéré comme l'un des pères du deep learning et donc une sommité en intelligence artificielle, évidemment. Et j'ai fait comme nos étudiants. J'ai demandé à ChatGPT, fais-moi une bio sur Yann Lecun. Et au moins, là, d'abord, je le dis, hein, les étudiants, vous voyez, je dis, c'est ChatGPT qui a travaillé, c'est pas moi. Donc, je cite mes sources. Et puis, en plus, j'ai le moyen de vérifier ce qui a été comme résultat. Donc, je vais lire ce qui a été dit, et puis Yann nous dira si c'est correct ou pas. Je pense qu'il manque des choses. Bon, forcément. Déjà, j'ai remarqué qu'il y a des différences entre les versions anglaises et françaises. On ne met pas l'accent sur les mêmes choses. C'est intéressant. Donc, ChatGPT me dit que Yann Lecun est un ingénieur en informatique et un chercheur en intelligence artificielle français. Il est connu pour son travail sur les réseaux de neurones convolutionnels, CNN, et leur utilisation dans la reconnaissance d'images et la vision par ordinateur. Il est actuellement professeur de recherche à l'Université de New York et directeur de l'intelligence artificielle en sciences de la vie et de la santé à Facebook. Il a également été professeur à l'Université de Princeton et à l'Université de New York. Il est membre de l'Académie des sciences américaines et de l'Académie des sciences françaises. Il a reçu de nombreux prix pour son travail, notamment le prix I3E de Neural Network Pioneer en 2016. Est-ce que c'est correct, Yann? Voilà, plus ou moins, c'est bien ce qui me semble. En particulier sur la position actuelle, je crois que, si on peut se tutoyer, tu as quitté la position de directeur et tu es chef scientifique en intelligence artificielle dans la même boîte. Donc, ce n'était pas complètement à jour. Et puis, à citer un titre, je ne sais pas si j'aurais pris celui-là en termes de prix. Je pense que le prix Turing, qui est considéré comme le prix Nobel en informatique, puisqu'il n'en existe pas, comme en maths d'ailleurs, je ne sais pas si c'est pour les mêmes raisons qu'on raconte pour les maths d'ailleurs, qui n'est pas de prix Nobel en informatique. Et donc, voilà, le prix Nobel qui a été reçu en 2018, je crois. Voilà, donc... on est content d'écouter cette conférence et puis je te laisse la parole.
Merci beaucoup pour l'introduction, c'est un vrai plaisir d'être ici. En fait, c'est ma première conférence en personne en Afrique et ma première visite au Maroc aussi. Un grand plaisir. Donc, je vais faire comme Eric et passer à l'anglais, sauf si vous me dites qu'il vaut mieux que je parle en français. Voilà, alors je vais faire deux conférences, donc une aujourd'hui et une demain. Celle d'aujourd'hui est plutôt une espèce de revue d'un petit peu tout ce qui se passe en IA, de résultats intéressants, pas technique du tout, donc un peu superficiel. Demain, la conférence sera un petit peu plus sur le futur, sur les défis, et sera un petit peu plus technique. Ok, maintenant je passe à l'anglais. So what can AI do today? And what can it not do? How can we go beyond? And how can we go beyond is more the topic of tomorrow's conference, but tomorrow's talk. Today is more about the state of the art. Okay, yeah, I don't see my slides here, but I think that's okay. Today most of the applications of AI use machine learning. Most of those applications use deep learning, and most of applications of deep learning use supervised learning. But increasingly, a lot of applications use a technique called self-supervised learning. So we've just heard of ChatGPT, but there is a long history of work in this area. So I'll talk a little bit about that. But supervised learning is really the workhorse of a lot of applications in AI. And it's a very simple idea that goes back to the 1950s of essentially having a collection of samples, inputs and outputs, and you train a system to produce the output you want for every input in your training set. Thanks. So, for example, you want to train a machine to classify images. You show an image of a car, and you produce the answer with the machine, and you see if the answer is car. If the answer is car, you do nothing. If the answer is something else, then you adjust the internal parameters of the system so that the output gets closer to the one that you want. That's supervised learning. And this works really well for things like speech recognition, image categorization, translation, things like that. But increasingly, it's being replaced by another phase of learning called self-supervised learning. So the problem with supervised learning is that it requires a lot of data. But the advantage is that you can train seemingly oversized parameterized systems like large neural nets, deep neural nets, and it still works, even though statisticians in the past would have said it cannot possibly work because your system has too many parameters for the number of samples that you have at your disposal. But in practice, there's some somewhat mysterious phenomenon called double descent that makes the system generalize to new examples pretty well, even though it has many more parameters that would seem reasonable. So that's a case where theory was formally right, but there is a condition where it's wrong, and it actually, this sort of idea that neural nets could not possibly work because of theory held back the field for a long time. Correct me if I'm wrong, Eric. But it's a very strange phenomenon in the sociology of science. Okay, so formally, of course, we all know that supervised learning mathematically can be formulated as the minimization of some objective function. That objective function, or cost function, computes some sort of divergence between the output that you want for a particular input x. You want the output y, and the system is going to produce an output y tilde or y bar. And you're going to measure the divergence between the two. And if you average this over a large number of samples, you get a cost function. And the name of the game in supervised learning is to find a value of the parameter that minimizes this cost function. Or if you want to do Bayesian neural nets, you have to do something a little more complicated and sort of produce a distribution over parameters, not a single point, and then sort of marginalize over it. But that's a bit expensive for large neural nets. And for that optimization process, we use gradient-based methods. So methods by which we compute the gradient of the loss function with respect to the parameters and then take a step in the negative direction of the gradient. And so this is like walking down a landscape in the mountains and basically not being able to see around us except in the immediate surrounding. And we just follow the direction of steepest descent and sort of keep going down, and eventually we'll converge to the valley. But instead of two parameters, we may have a lot of parameters. So the basic architectures of the simplest type of neural net is one in which we stack alternated layers of linear operations and nonlinear operations, pointwise nonlinear operations. So the linear operation basically comes down to taking a bunch of inputs, computing a weighted sum of those inputs with weights, and then do this with multiple sets of weights. So we compute sort of multiple weighted sums of the inputs, and then we pass those results to scalar nonlinear functions. The ones that are most popular are very simple ones, like what's called a ReLU, which is really a half-wave rectification or a positive part, if you want. And you can prove that with just 2 layers of linear, nonlinear, linear, so it's 3 stages. You can approximate any function you want as close as you want, as long as you have very many units in the middle layer. Unfortunately, or perhaps fortunately, most complex functions that people want to approximate, things that do image recognition or speech or something like that, require actually more layers, unless you're willing to spend an enormous amount of resources having a very, very large middle layer. So again, that's a situation where the theorists for years told us, like, why do you want multiple layers since you can do everything with 2 layers? It turns out having multiple layers is way more efficient. And so, which theory had kind of trouble really kind of capturing, if you want. So the basic operation of linear weighted sum and nonlinearity can be seen as a very approximate emulation, if you want, of what neuroscientists observe in the brain, but it's extremely simplified. But it has a bit of the same character, and of course, learning takes place by modifying the weights in the weighted sums. And to do this, we need to use gradient descent. So we need to be able to evaluate the gradient of the objective with respect to all those parameters. For this, we're going to use incredibly sophisticated concept in mathematics called chain rule, which was invented by Newton and Euler and Leibniz and all these guys. So it's not recent. It's not like the latest in mathematical sophistication. But it's a basic idea that if you have a functional module that takes an input, produces an output, and then you stack another one on top of it, and you want to compute the gradient of some objective function, regardless of what it is, with respect to the input of the first module, you have to basically multiply by the Jacobian matrix of all the modules going backwards. And that's just a practical application of chain rule. Now, this is well known in mathematics and engineering for many decades, but it's only around the mid-'80s that people demonstrated that this could be used for machine learning in very efficient ways. And the reason it took so long is because people sort of didn't think in the right way about how gradient descent basically could work so well. So it came late, even though it's conceptually extremely simple. And there was a bit of a disbelief for many years that this could work so well because it was so deceptively simple. Being able to compute gradients easily by assembling blocks in a kind of a software form, the general idea for this goes back to the early 90s, that you can kind of assemble functional blocks, and as long as every block knows how to compute its output with respect to its input, and knows how to compute the gradient of some function with respect to its inputs, if it knows the gradient with respect to its output, that concept and software to implement this was sort of independently developed in the context of neural net research in the early 90s, and in the context of what's called automatic differentiation in numerical scientific computing, essentially. But the systems that we use today, like PyTorch and TensorFlow and things like this, and JAX, are the direct descendants of those early systems. Okay, the next thing you can ask yourself is, what architecture do I have to give to my system? Of course, I can have lots of neurons in every layer, and I can connect them to, every neuron in one layer can be connected to every neuron in the previous layer. But the magic of deep learning comes when you give some structure to the network. You connect them in a particular way so that you take advantage of the regularity in the data, and that's really what convolutional networks are. So their architecture is inspired by two things. One is classical signal processing. The idea of convolution is very much comes from classical signal processing, but also neuroscience. When you look at the architecture of the visual cortex, you realize that neurons in the early areas of the visual cortex in the back of your brain are connected to your retina indirectly, and each neuron only looks at a small area of the visual field. And there are many neurons that basically perform the same operation on different parts of the visual field. So that's the idea of sort of replicating the same neuron over a visual field. Convolutional nets basically are kind of a conceptualization of this idea. So the operation that's performed by a convolutional net here, the basic convolution is you take an input and you have a set of coefficients here. You compute the dot product between a window over the image and those coefficients, and that gives you the weighted sum for this neuron here. And then you take that window and you shift it over every location on the input, and then record the results. That's called a discrete convolution. Technically a cross correlation, but it doesn't matter for our purpose. And so each of those maps here is a result of applying a convolution to the input, and you get different results because the set of weights are different. And then you do another operation called pooling, where you basically take a small neighborhood of activities in a feature map, and then you compute their average or their maximum or any kind of aggregation of the values, and then reduce the resolution here by a factor of 2. And then you repeat the process. So again, you have convolutions. Of course, there is a nonlinearity, which I forgot to mention after the convolution. And then again, pooling. And you keep kind of stacking layers like this until you get to the output. And we built things like this in the late 80s and early 90s, and they work really well for things like handwriting recognition. So this is the internal activity of neurons inside of this convolutional net. I'm not representing the output here, but this is to show that the representation is somewhat robust to kind of change in position and perhaps distortion. We'll see some more examples after. This is a short video that was shot in early 1989 of a demo system that was built at Bell Labs. So the person you saw here is me when I was 29 or 28. And so we put the system under a piece of paper under a camera, and I hit a key, and the images are captured and sent to a specialized DSP board that could do this calculation fast enough at the time because computers were pretty slow. And could recognize characters of various types, including fairly exotic ones. So this was with a processor that was capable of 20 million operations per second in floating point. Your smartphone is thousands of times more powerful than this. This is Donnie Henderson, the research engineer that actually put the demo system together, Rich Howard, who was the lab director. Soon we realized that we could use this not just to recognize individual objects, but also multiple objects, and without having to separate the object beforehand. That's called image segmentation in computer vision. And so we're able to essentially build systems that could recognize multiple characters, and this had some practical applications in the mid-90s on things like reading checks and various other documents. The last author here is Patrick Hafner, who is, I guess, was at CNET in Lannion simultaneously with you, Eric. We were talking about this yesterday. Okay, and then what happened in the late 2000s, early 2010s is that GPUs appeared, and our friends at University of Toronto were able to implement, to make a very efficient implementation of convolutional nets on GPUs and produce AlexNet, so a convolutional net whose architecture was not hugely different from the early ones, but it was much, much bigger, more layers, more feature maps, more convolutions, a few tricks that appeared in the meantime. And this really sort of changed the mind of a lot of people in computer vision, but also in other areas, that now neural nets really worked, and you basically could not ignore the good results that they had always produced, but could no longer be ignored. And that kind of started really a revolution where a lot of people thought about all kinds of applications of neural nets, convolutional nets in particular, and more generally deep learning, which is sort of a slightly more general concept than deep neural nets, but very much the same thing. So of course in transportation, driving assistance, or semi-autonomous driving, online safety and security, content filtering and things like that, environmental monitoring, medicine, and science. So I'll go through a few of those, some of those applications. Perhaps the biggest application of deep learning today is in companies like Meta and Google, where deep learning is used absolutely everywhere to do content moderation, content filtering, and ranking. So whenever you connect to Google and do a search, or any search engine, the spam is being filtered out by deep learning systems. The ranking of the search is done with deep learning system increasingly, or at least neural nets. It has to run really fast. Same when you connect to Facebook or Instagram. The most challenging task is actually content moderation. So you have to take down all kinds of illegal content, like hate speech, terrorist propaganda, child exploitation, things of that type. That's required in a lot of countries, and you have to use AI systems for this, and they do a pretty good job. In fact, there's been a huge amount of progress in things like hate speech detection over the last 2 or 3 years because of progress in natural language understanding, thanks to things like transformers, which I'll talk about a bit later. So the entire tech industry now is built around deep learning. If you try to rip deep learning out of Google, YouTube, Amazon, etc., Meta, those companies crumble. Their service can't work without it. But then deep learning can be used for a lot of things, and things like erasing cultural barriers by being able to translate effortlessly between hundreds of languages. I'll come back to this technology. But also to bring technology to people who would have trouble accessing it because, for example, they can't read. So if you have a system that can recognize and understand voice and synthesize voice, you can interact with voice with the digital world and without necessarily knowing to read. With multilingual system, you can speak in your own language or in your own dialect, possibly. And we know that there are thousands of dialects around the world that people use daily. 800 million people are illiterate around the world. 300 million are visually impaired. And so AI is going to be a big change for them. So things like content filtering that I was referring to earlier, content moderation. This has to be done on social networks. You can't avoid it. Even though Elon Musk for a while thought he could avoid it, he realized he can't. So things like a few statistics, for example. This is for early 2022 on Facebook. About 95%, a little over 95% of hate speech that is being taken down by Facebook is taken down preemptively by AI systems before anybody sees it. The scale of the volume of data is so much that this cannot be done by hand solely. There are content moderators, but most of it is done automatically, and it has to be done in hundreds of different languages. There are countries where people kill each other because of some war or something, and you have to do what you can to stop people from calling for violence and things like this in all kinds of local languages. It's very, very hard. It's a huge challenge for AI. But it's made a huge amount of progress in the last few years. So the prevalence of hate speech on Facebook is about 0.02%, which is too high. It's still a lot of posts, right? But it's much smaller than it was just a few years ago. And then, for other things as well. Detecting terrorist propaganda and nudity is fairly simple, but hate speech is much more difficult, and also it depends what your definition of it is. Okay. So for image understanding, this is a short video put together by my colleagues at FAIR a couple of years ago that demonstrates the capabilities of current vision systems. So with vision systems, we can detect and name individual objects in images, put a box around them, estimate the pose of people more or less in real time. But more interestingly, over the last few years, it's become possible to do what's called semantic segmentation or panoptic segmentation or instance segmentation, which means basically drawing an outline of every object and then naming the object. and the background objects as well. So that's called panoptic segmentation. And that opens the door to a lot of applications of computer vision in social networks, but also in driving assistance, in medical image analysis. So by the way, the system is called Detectron2, and it's available in open source. So you can just download the code. And I'm not able to switch. Here we go. Okay, a lot of applications, of course, in medical image analysis and they use those techniques. So very similar to the demo I showed earlier of multiple character detection, character recognition without prior segmentation. What basically happens here is that you have a large convolutional net that looks at the entire image, and it produces a feature map on the output. For every location, every window on the input, it tells you what it thinks it has seen at that location. And it can also produce a guess as to where the actual position of the object you are interested in is within its viewing window. And it does this for every window on the input. And so, obviously you can apply this to large images at high resolution and detect kind of small motifs, which is what you need to do for medical image analysis. And those systems can also work with 3D images. So they're not limited to looking at the display like humans. They can actually take, if you use MRI or PET scans or CAT scans or something like this, what you get is a 3D image. And some of those systems can just take the 3D volume directly and interpret the image that way. So you can detect breast cancer, for example, more efficiently if you have a 3D image or if you have multiple views rather than just a single one. This is work by the group of one of my colleagues at NYU called Christophe Guerras. He's a machine learning person, but working in the radiology department at the medical school. Okay. This is some work that was done in collaboration with the NYU radiology department and FAIR, Fundamental AI Research at Meta, so my colleagues a few years ago. And the idea there was to use deep learning to basically exploit the redundancy in the data, in MRI data, for example. So this is the example of MRI of a knee for knee replacement surgery. And the problem with MRI is that you have to lie down in a machine, noisy machine, and not move for maybe half an hour, 40 minutes. And this system can reduce this to about 10 minutes without loss of quality in the image, which means that the cost of the medical exam is greatly reduced, and more people can get the same test now because it's cheaper. And so this technique called Fast MRI was open source, given out for free, and a lot of companies now that build MRI machines are actually incorporating such systems, software inside of their machines, so they're available to everyone. And there's a bunch of articles on this in the press. Here's another application. So this is applications of convolutional net in particular, but also other models to science, in particular to neuroscience. So the best models that people use now in neuroscience to explain what they observe in the functioning of the brain, particularly the visual cortex, is a convolutional net. So you train a convolutional net to recognize images, and then you show an image to the convolutional net, and you show the same image to a person lying down in a functional MRI machine, and you record their brain activity, and you try to explain the brain activity that you observe with the activity you observe in various layers of the convolutional net. And what you notice is that certain areas, or the early visual cortex area, are explained by the low levels in the convolutional net, and then the higher level areas, what's called V2, V4, and inferotemporal cortex, where objects are represented, are better explained by the higher level in the neural net. So there seems to be kind of a similar hierarchy in the visual cortex as is used in convolutional nets. And there's a lot of really interesting papers about this. This is a recent paper by some of my colleagues in collaboration with CNRS and the Neurospin, Charlotte Cocheteux, who's a resident PhD student at FAIR in Paris, and Alexandre Grandfort and Jean-Yves King, who has a dual position at FAIR in Paris and CNRS, where they what they use there is actually a transformer system, so similar to the systems that are used for natural language understanding to explain the kind of activity they see in the brain when someone is being told a story and asked to remember the story so they can explain it later. So it's kind of testing, understanding. And what they notice is that it's not as good as what we observe in visual cortex with convolutional nets. So transformers only partially explain how language understanding occurs in the brain, but not well enough, if you want. So there's a lot of mysteries of things that go on in the brain that are not explained by current models, really. Another application of neural nets, convolutional nets in particular in neuroscience, is for connectomics. So basically reconstructing the microcircuit in a piece of brain tissue by segmenting every neuron and identifying every synapse. This is a project that was started by Sebastian Song about 15 years ago at MIT. He's now at Princeton. And they can now essentially reconstruct the entire diagram of a piece of brain of the fly, for example, entire brain, or a small piece of the brain of a mouse, or something like this. The volume of data is so high that you can't do an entire mouse brain yet, but let alone a human brain. But then the long-term dream of this is that you could reconstruct the entire wiring diagram of a human brain, and then perhaps simulate that brain on a very, very fast computer. Okay, this is completely outside of what's possible today. The volume of data is just enormous. But this is what people kind of, think about in science fiction when they say, upload your brain to a computer. Right? It's not even clear that might work in principle, but certainly in practice, it's completely out of range. Also, it's destructive. Okay, so you have to slice your brain for this to happen. A very interesting development of application of AI to science, particularly using transformer architectures, which I'll talk about a little bit later, is protein folding and protein science in general, or biochemistry. So of course, many of you have heard of AlphaFold and AlphaFold 2. There's sort of parallel work at FAIR called ESM-Fold and ESM-Fold 2. And those are systems that, using large neural nets, basically using very similar techniques that are used in the context of natural language understanding, but with a lot of specific methods for proteins. Those are methods that can predict the 3D structure of a protein from a specification of the sequence of amino acids, right? So you give the system a sequence of amino acids, which are symbols, okay, like letters. And the system kind of figures out how it's going to fold and what the configuration in 3D of that protein is going to be. And that's very important because the shape of the protein determines its function. It determines where it's going to stick on another protein or some sort of site. And so the potential impact of this in things like drug design, but also medical science in general, biomedical science, is really enormous. So what's happening now is the sort of reverse process that people are working on of essentially being able to specify a shape that would correspond to a site that you want a drug or something to bind with. And then through inverse folding, the system tells you what sequence of protein, what sequence of amino acids would produce a protein that has the right shape. So that would be kind of drug design. Okay, that opens the door to enormous potential. It's not realized yet. People are still very much at the research level. So this is a slide that describes the ESM and ESM-Fold project at FAIR. It's a small group that works on protein folding at FAIR. And they've produced something called the ESM Atlas, which is basically an atlas of 615 million proteins, all of which have been folded using ESM-Fold. And some of those proteins are very rare. We don't even know where they come from. Basically, you take, a little bit of water from the ocean or a river. You break up all the DNA that's inside of it. You detect which parts are genes that produce proteins, and then you sequence all of those. So that gives you an enormous collection of proteins, but you don't know which organism they come from because it's all mixed up. But you know that protein exists somewhere in nature. There's about 600 million of those, and that was done over the space of a few weeks because ESM-Fold version 2 can work really fast, and it's all open source and everything. A lot of applications of deep learning to physics, particularly filtering trajectories or interpreting trajectories for high-energy physics experiments in particle accelerators, complex simulations of fluids or aerodynamics or atmosphere and oceans. It's very interesting for climate modeling, for example, climate change modeling in particular. In astrophysics also for performing statistics on different types of galaxies that would be compatible or incompatible with different ideas, theories of how the universe started or the density of dark matter or things like that. And then fantastic applications in material science and chemistry, where with deep learning model, you might be able to predict the properties of new materials. That would be very interesting for a lot of things, for displays, for example, for batteries, and for a particular application that some of my colleagues at FAIR have been working on, which is sort of an open research project. It's collaborative, you can participate in it. It's kind of an open competition if you want. It's called the Open Catalyst Project. And the goal of this project, which is a collaboration between FAIR and Carnegie Mellon University, is to design new compounds, new materials, new catalysts that can facilitate the separation of hydrogen from oxygen. So here is a fact that I'm sure many of you are aware of. You could cover a small part of the desert just down the street in Morocco with solar panels. Okay, when I say a small part, it's not that small, but it doesn't need to be very large, and produce enough energy for the entire world. Okay, I mean, certainly for the entire country, but perhaps the continent, but possibly for the entire world. Very sunny Morocco. And the problem with that is that we don't know how to store the energy whenever the sun shines. And so what needs to be done is technology where we can put photovoltaic panels wherever there is sun, have them produce energy whenever there is sun, and then store this energy at a very large scale. The best way to store energy is in the form of hydrogen or methane. Okay, so you take some water from the ocean or whatever, and with electricity, you separate hydrogen from oxygen. And then the hydrogen, you combine it with carbon or something to produce methane. Then you can ship the methane wherever it's needed. I'm not saying that is easy either, but it will be possible. Now, the problem is we have two sets of methods for separating hydrogen from oxygen with electricity. Some of those methods are efficient, but not scalable because they require catalysts like platinum, which are too expensive and rare. And the other methods are scalable, but not efficient. Okay, so what we have to find is a catalyst that is cheap, widely available or can be produced, that will catalyze this separation of hydrogen from oxygen. And perhaps we can use AI to help us do this. So that's the purpose of this open competition. If we solve that problem, we've made a big step towards mitigating climate change. The potential impact is very risky. It may not work at all, but it's worth a shot because the payoff could be enormous in terms of progress for humanity. So if you have any interest in this, I really encourage you to kind of dig into this project. Here is a slightly more frivolous application of AI, which is generative AI. So this is a system that was put together a few years ago, like last year, by my colleagues at FAIR, called Make a Scene. You basically type a text and perhaps draw an approximate sketch of an image, and then you wait a minute or so, and the system generates images that correspond to your textual description as well as the sketch that you drew. And by the way, this system was produced before all the ones you've heard about. So this is from March 2022. You might have heard of DALL-E 2, that was April 2022, and ImageN from Google, that was in May 2022. So there's a lot of companies that are working on those things. Some of those companies make those technologies widely available to the public. Some of them don't because it's not their main line of business, and they don't need that to, kind of make use of the technology. So generative technology like this is going to make a huge impact on sort of creativity. It's going to help a lot of people who are not good artists at the moment because they don't have the technique to actually produce content, which you could post on social networks or whatever, or you could decorate your house with, or if you are a business, you can generate advertising or something like that, or design products using generative art. You can do crazy stuff, right? So images that look more or less realistic, a man standing next to a woman in a room, but you can also do things that are kind of crazy, a laughing purple porcupine, or a teddy bear with a blue scarf and eyes tilted to the left. I mean, there's a lot of details, or a zebra riding a bicycle whose wheels are made of pizza, whatever. You can do kind of crazy stuff, right? And then, because those systems are stochastic, you can make them generate multiple types of images from the same input. They take, basically a source of noise, and depending on that noise, you can think of this as inspiration. The noise kind of generates multiple outputs that are all kind of somewhat consistent. So how does that work? So the way the system is trained is that it's fed with a textual description. It's fed with an image, okay, a photo, or painting, or drawing, together with a textual description of that image, and with a segmentation map produced by a vision system like the Lecun.Prof that I was showing you earlier. So all of that goes into encoders that turn those into basically a bunch of vectors. You can think of it as, every input text or image is turned into a sequence of vectors that are actually quantized, but that's kind of a detail. And then all of that goes into a transformer, a large neural net architecture that is trained to produce, again, a sequence of vectors that can be decoded into the original image, okay? So that you can guarantee that there is enough information inside of the representation so that you can reconstruct an image from it. And then there are various tricks to make the image kind of look nice and have high resolution. So this is before diffusion models and stuff, right? So now there's like two or three techniques to do this. That's a particular way of doing it. I think I switched one. Yeah, so here's another example, a colorful sculpture of a cat. And then the sketch is actually a kind of a drawing of a cat, and then the system kind of puts a texture on it. And somewhat, those images can be realistic, a side view of an owl sitting in a field, a close-up of a cat with blue eyes. You can do a lot of stuff with that. So it opens the door to a lot of creativity. Of course, this is, Facebook and Messenger and WhatsApp, so you want to generate stickers and things like that. So those techniques can be used for that, and they are kind of somewhat, how would you say, compositional, in the sense that you can take an original image and then manipulate it with the prompt. Here's an avocado, and you say, needs to have red lipstick, and the avocado now has red lipstick. So slightly frivolous, but fun. So you can sort of generate various combinations of images. So that's coming probably, fairly soon at a social network near you. Sticker creation and things of that type. Okay. I don't seem to be able to switch slide until the video ends. Strangely enough. Oh, here we go. Okay, so this is another extension of this, where now you don't generate fixed images, but videos, short videos, and then over the next few months and years, there will be the capability of generating longer videos by basically just writing a script, so you could generate entire stories and things like that. And those systems are not perfect yet. Very often, when you ask them to produce humans, those humans have hands that look funny. They have more fingers than 5. They're a little strange, but it kind of works more or less pretty well. And you can make a fish swim, or a robot dance, or a sailboat on water and things like that. So those are entirely generated from text. Again, so this is a thing. Okay, now let me switch gear a little bit and talk about limitations of current AI systems. Particularly, we've heard a lot in the last few years about reinforcement learning, and a lot of people thought that because we could train systems to play Go and chess and various video games with reinforcement learning, it would be kind of a path towards human-level AI. And that turned out not to be the case, because reinforcement learning is very inefficient. Reinforcement learning today requires a very, very large number of interactions of an AI learning agent with the environment for it to learn anything. Which is why we cannot currently use reinforcement learning to train, for example, a car to drive itself. Most of us here can learn to drive a car in about 20 hours of practice without causing any accidents for most of us. We still do not have completely autonomous self-driving cars, at least none that work purely from vision. And the reason is because our learning techniques are too weak compared to the type of learning techniques that animals and humans seem to use, or learning paradigms, if you want. So to give you an idea there, you can train DeepMind trained a system to play StarCraft, the strategy game. But training it to play a single map required the equivalent of 200 years of real-time play. Of course, you can do this fast on the computer, but it's large. The best Go players take a very long time to learn to play Go. They have to play millions of games against themselves. How is it that humans can learn to drive a car in 20 hours? If you were to use reinforcement learning, at least the current crop of reinforcement learning, or at least the crop until fairly recently, to train a car to drive itself, the car, before it trains, doesn't know that if you drive next to a cliff and it turns the wheel to the right, the car will run off the cliff and then get destroyed, and the passenger is probably killed. It doesn't know. It has to do this multiple times before it realizes it happens. And when I say multiple times, it's probably thousands of times. And then it has to do it a few more thousand times to realize how not to do it, how to avoid to do it for this particular cliff. And then it has to do it a few thousand times for another cliff. And then you don't know if it encounters yet another cliff, it's going to be able to decide that you don't want to run off that cliff. So that's why we don't have self-driving cars. Okay, we don't have the techniques that allow an 18-year-old to use its knowledge of how the world works to learn to drive safely in about 20 hours of practice. And that's a big limitation. So this is what I will talk about tomorrow. How perhaps we can go beyond those limitations. But it's basically because machines don't have what we call common sense. So how to get machines to learn common sense? And this is a kind of an important question to answer, because eventually, currently we all have one of those or two of those in our pockets. But perhaps 10, 15 years from now, we'll be wearing augmented reality glasses that will display information on top of the real world. And we'll be interacting with those glasses through a virtual assistant, or personal chief of staff, if you want, right? So everyone will have an intelligent assistant to help them in their daily lives. and they will interact with it through voice, but also through various other interaction schemes, which I'm not going to go into. And those AI systems will basically need to have more or less human-level intelligence because they will serve the same purpose as a human assistant. They will take care of a lot of stuff for us that we don't want to spend time on. They will, inform us. They will manage all of our interaction with the digital world. So, we're not going to have, Google and Facebook and Instagram anymore. It's our assistant that will kind of fetch the information that will help us and filter the information that we'll consume every day. So we need machines with common sense. We also need machines with common sense for self-driving cars. We need machines with common sense for domestic robots and things like that. So it's an important scientific question, but it's also an important question, practical question, if you want, in the future. So how is it that humans and animals learn so quickly? And how could machine learn so quickly? Again, that's the topic of my talk tomorrow. But basically, humans learn by observation, a lot by observation, also by interaction, but a lot by observation, without being taught. Babies learn how the world works in the first few months of life, and they just learn it. They don't need to be talked to. Animals learn it without language. Some animals learn it without even interacting with other animals of the same species. And it's all based, perhaps, on something I call self-supervised learning, but other people have called different things. And so basically, you have a piece of data, you corrupt it in some way, possibly by removing a piece of it. So for example, I give you a video clip, and I only show you the first part and not the last part. And then I train a system to fill in the blanks, okay? Predict the part that is missing. And so this would be self-supervised learning. And most of learning that occurs in nature probably is of that type. It is not supervised learning, and it is not reinforcement learning. There is supervised and reinforcement learning in biology, and we give it a lot of importance, but it actually plays a minor role, in my opinion. Most of learning, most of your synapses are trained using self-supervised learning, not using supervised nor reinforcement. Because supervised learning and reinforcement learning are so inefficient. So here is an example of enormous success of self-supervised learning, and it's in the context of natural language understanding. So take a piece of text, remove some of the words, or replace them by other words, okay? And then take that corrupted piece of text, feed it to a very large neural net, which is generally a transformer architecture, and then train that system to reconstruct the missing part of the text, so basically to predict the words that are missing, okay? This is a special case of what people used to call a denoising autoencoder. I actually had some work in my PhD thesis on this back in 1987. There's some more recent work by Pascal Vincent from Mila in the mid-2000s, but it's really kind of completely taken off over the last few years in the context of NLP. So this is, you've heard about BERT. This is the type of training that BERT basically popularized. But there were kind of similar work before by Renan Colobert and Jason Weston, for example, in around 2010, where they had kind of techniques of that type to pre-train NLP systems. And when you use those techniques and you combine them with an idea that was inaugurated by some of my colleagues at FAIR in the early days of FAIR in 2014, called memory networks, memory augmented networks. So this is kind of a circuit, a particular type of neural net that basically is an associative memory. So it has keys, and you feed a query to it. The query is compared with the keys, the key vectors. And then the coefficients that come out of it are normalized, and they are used to compute a linear combination of value vectors. And that corresponds to some sort of associative memory, and you can backpropagate gradient through this. You can train the keys and the values and backpropagate through the query. So they had a couple of experiments, early experiments with this in 2014. And this is an example of what's called an attention circuit, if you want. And then Washwani at Google in 2017 proposed this with a paper whose title is Attention is All You Need, the transformer architecture that basically takes this to the extreme and builds an architecture where you have associative memory circuits of this type, but the keys and the queries are both input tokens, right? So you have a set of input tokens, and you use n-1 input tokens as keys, and the remaining one as a query. And so you compute the matrix of all the dot product of all the inputs with them. And then you take that big matrix of scores, you normalize it across columns or something like that, and you use those as coefficients to compute linear combinations of value vectors, and then you stack multiple layers of those. And what you have is basically a neural net that can dynamically rewire itself using those dot product that basically determine where the signal is going to go, and then store an enormous amount of information in this associative memory. And it has an interesting property, which is that the same way convolutional nets are equivariant to translation. So if you take an input to a convolutional net and you translate it, the output will be translated, but otherwise unchanged. Okay, so that's the notion of equivariance. Transformers are equivariant to permutation. So if you take input tokens and you permute them in any permutation, the output will be permuted, but otherwise unchanged. So this is the ideal type of architecture you want to use when the inputs that you're manipulating are objects, and what matters are the relationship between those objects, but not their position, for example, right? But in fact, you can put some position inside using something called positional embedding. So anyway, this architecture is very powerful, and it's been applied to all kinds of stuff, including computer vision, and they work really well. So this is a use of transformers that was proposed by some of my colleagues at FAIR, Guillaume, who's in Paris, Alexis Kono in California, a couple of years ago. And it's a multilingual transformer system that can essentially, you can train it mostly on monolingual data, and it will produce encoders and decoders that can translate from any language to any language. This idea has been pushed a lot by some of my colleagues. This is some other work of using transformers to do symbolic mathematics, which I'll skip. There's a lot of interesting work over the last couple of years on this, actually, but this was kind of inaugurated by Guillaume Lample and François Charton from FAIR in Paris. You can use those transformers for dialogue systems, including dialogue systems that are informed by images. So they can look at an image, produce a representation of that image, and then generate a dialogue on this. This is a couple of years old. It's called Multimodal Blenderbot, Blenderbot. Blenderbot is a series of chatbots that Meta and FAIR has been producing. They're not as widely available as ChatGPT, but they've been around for a while, so there's a big group working on dialogue systems at FAIR. So that's an interesting point, actually, that I've made on Twitter over the last few days and attracted a bit of attention, which is that from the scientific point of view and technology point of view, ChatGPT is not particularly innovative. It's a nicely put together system, nicely engineered for dialogue and large language models, and it's not too big, so it can be run and made available publicly. But scientifically, there's, as far as we can tell, there's not much innovation in it. It's just interesting to put it in the hands of people and have people have positive reaction to it, because before that, the public's reactions to this dialogue system was actually very negative. As I said, those transformers can be used for computer vision. This is a project called DETER from a couple of years ago by Nicolas, who is now a research scientist at FAIR, that can do a really good job. So it has a front end that is a convolutional net, and then the back end is a transformer that does sort of the object-based reasoning at the back end and does a really good job at things like panoptic segmentation and stuff like that. This is OPT175B. It's a large language model and transformer that can be used for all kinds of applications in natural language understanding, produced by my colleagues at FAIR. It's very similar to GPT-3, if you've heard of that. The difference is that this one is open source, so you can just download the code and even the coefficients, and apply it to all kinds of tasks. And it will predict if you use it as a large language model. You give it a prompt, and it will kind of complete it. The difference with the current version of ChatGPT is that this has not been refined through user interactions. So So in that sense, it's not as good. Here's another example, no language left behind. So this is, again, using transformers and various self-supervised learning techniques to train systems to translate languages in each other. This system can translate 202 languages in any direction. But the interesting thing is that we only have parallel text for 2,400 of the language directions among all 40,000 possible directions. So you have very, very sparse training data, right? You don't have parallel text between, the local dialect spoken in Marrakesh and, some language in the middle of sub-Saharan Africa. But you don't need to, because you might have parallel text between languages that are very similar, or those languages, and, for example, French or English. And there is enough redundancy between neighboring languages, like Arabic or something, that, or Berber or whatever, that the system is able to kind of interpolate, essentially. So this system can translate 200 languages in any direction with pretty good accuracy. It's a model with 54 billion parameters, which is not that big. And these are all the languages it can translate. And I'm sorry that some of them are cut. I don't see Berber here, but that's a lot of languages, and some of which I'd never heard of, and I don't know where they are from in the world. SSL can be used for speech recognition. We can now train a speech recognition system with only about 10 minutes of labeled data, which means now we can have speech recognition systems for rare languages for which we don't have a huge amount of data, and local dialects. In fact, there was a project, I don't have a slide on this, from my colleague in Paris called Textless NLP, which basically allows to have translation systems that work directly from speech. And those work with languages that do not have any written version. Okay, so there are dialects for which there is no writing. But we can use a combination of speech recognition without actually having to go through text to be able to translate those languages directly into other languages, speech to speech. It's pretty amazing, actually. So it doesn't work for images, so I'm going to skip this because I'm going to talk about this tomorrow and just go to conclusions. Self-supervised learning really is the future of machine learning and AI. It's going to be increasingly used. It's already bringing about a lot of progress, but it's going to produce the next revolution in AI, I think. But we need systems that are capable of reasoning and planning, and none of the current AI systems are capable of that, with very few exceptions, mostly for things that can play games. And so this is a bit what I'm going to talk about tomorrow. Can we get machines to learn like animals and humans? I think so. It may take a while, though. It's not for tomorrow. Will machine ever reach human-level intelligence? To me, the answer to this is absolutely yes. There is no doubt we're going to have machines that are as smart as humans in every domain where humans are smart. Should we call this artificial general intelligence? And my answer to this is no, because human intelligence itself is very specialized. We think our intelligence is general, but it's not. It's very specialized. Computers are much better than us at many tasks, and that shows that we are specialized. Before we talk about human-level intelligence, we should talk about rat-level or cat-level or dog-level intelligence. Cats and dogs are capable of very complex planning and reasoning. We don't realize this. We don't give them enough credit for it, but they are capable of planning. Just watch a cat trying to get on top of a piece of furniture, but kind of jumping onto various objects. Their planning abilities are amazing. No AI systems today can do this. So we will eventually have machines with superhuman intelligence, but it's not going to happen tomorrow. It's going to take a long while. Despite what you might hear from people who are overly optimistic, this is going to take a while. It's not simple. There's going to be obstacles along the way. Machines will not take over the world. It's a projection of human nature onto machines that has no object. And it's because intelligence is absolutely not correlated with any desire to dominate. At least it's the case for humans. It's not the smartest among us that are necessarily the leaders. we have examples of this on the international geopolitical scene every day. Thank you very much. I went a bit over time. I'm not sure there's time for questions. It'll be cool. So first of all, humans are also subject to adversarial attacks. They're just less sensitive to them, right? But visual illusions are the best example that we have of basically fooling the human visual system into believing something that doesn't happen. And we have thousands of those. So that's the first thing. It's a property of systems that have invariances, right? If you have any kind of mathematical function that has invariant properties, it's going to be invariant to certain transformations that you don't want it to be invariant to. Okay. It's also a consequence of the type of training that we're using. So in my opinion, a lot of vulnerability of systems to adversarial attacks is due to the fact that we train them with supervised learning. And we only train them to do a very narrow set of tasks. And so the system learns representations that are only appropriate and specific for that task, and as a consequence is easily fooled by going outside of the data manifold, if you want, right? So when you train a system with data that lies on a low dimension of manifold inside of the ambient space, you determine the function on that manifold. If you go just outside of that manifold, you haven't trained the function, right? So you don't know what the result is going to be. In fact, there's various papers on this. There's one actually by Shamir, you know, the S in RSA. He's got a couple of papers on that, actually, that explanation of adversarial attacks. So in my opinion, the increased use of self-supervised learning will actually mitigate those problems a lot. And the more general we make our machines, so the less specialized for narrow tasks, the less susceptible to adversarial attacks they will be. In vision, I think also this will be mitigated by systems that work from video and not just from still images.
So, yeah, you have a question?
With all the data that is generated today by AI, how can we prevent bias and ensure data quality for training our models in the future? Thank you.
Right. Yeah, the people are starting to ask themselves this question because, you know, we're starting to have pretty good generative models, and so more and more online data is going to be produced by generative systems, and then we're going to train generative, you know, we're going to train AI systems on that data. So there could be like a vicious circle. I mean, obviously, a good solution to this would be to have traceability for generated data. This is something we need to have anyway, because if you want to prevent kind of, you know, fake data to have an effect on society, you need it to be traceable. I mean, this is something that the younger generation that uses the internet has figured out, that before you believe something you read on Twitter or Facebook, you go investigate, like you ask for source, or you go search for something, is that true? You know, on Wikipedia or some reliable news or press or whatever, or scientific paper. And the older generation, though, is not used to that. So the people on social networks who are most susceptible to believe a piece of misinformation are people over 65. It's not the young. The young are used to be careful about it. But what we need is to help people trace the origin of data. And so that's going to be, you know, topic of primary importance, I think, in the next few years, and you're going to see sort of crypto-based systems for that. That's my guess.
Last question, yeah? Yeah, wait.
Thank you. I have a question in regards to the security parts of generated as an adverse effect of those models. So actually, I think that one aspect also that can be generated via those models is using them as cyber attacking ways. And it seems to me that right now a lot of systems do not spend a lot of money in securing the system and in guaranteeing its security. But through these models, it seems to me that more and more each system will need a state-of-the-art secure system in order to so what is your recommendation on that?
I mean, there's lots of different aspects to that question. So one aspect is like, do you need to make the AI systems themselves secure and protected against attacks and things like this, right? I don't actually think that's a huge problem, frankly. What's more interesting, apparently, is that AI systems today are used for security a lot. So the examples I showed, I mentioned some numbers of how Facebook, for example, uses AI for what's called integrity. So integrity means content filtering for illegal or objectionable content, but it also means things like protecting against spam and attacks of various kinds, false accounts. There's like billions of false accounts per year that are taken down by automatic AI systems. And some of them are rule-based, some of them use machine learning, deep learning in some cases. And so there is a big advantage of AI in security. But then the question is, how does that make certain systems vulnerable to use AI? So, for example, there was a bit of a kind of knee-jerk reactions when the first driving assistance systems were put in cars, and so now you have cars that have vision-based systems that can detect obstacles and brake automatically, right? That's called automatic emergency braking system, AEBS. And those systems are required in every car sold in the European Union today. So all new cars come with one of those systems. And the reason it's mandated is because it reduces collisions by about 40%. It saves lives. Okay, but a while back, people said, oh, if we have systems that can, detect people or stop signs or red lights and things like this, I can make this very minor change on the stop sign that will, make it will still be recognizable by humans, but those systems will actually get fooled and think that's not a stop sign and just, run through the intersection. And so people say like, oh my God, we're gonna, people are gonna get killed by this, by very simple attacks. The point is, you can paint over a stop sign today and fool humans, right? And people don't do this. Why would they do this? Even if they can, do it with less modification. Why would they do this for cars? You have to have a motivation to really kind of hurt people. Sometimes it's political, sometimes it's religious, sometimes it's some other reason, but there has to be some motivation. And today, people don't mess with road signs. Why would they do it? So there are certain, there's been a same kind of knee-jerk reaction when some of those LLMs were made available, where some people said, oh, now we're going to get flooded with misinformation. We're going to, and they sound right, so we're not going to be able to tell if a piece of information has been generated or not, and this is going to destroy the fabric of society, right? And I think that's just overreaction. Because people are smart, people adapt. The same kind of things were said when the printing press was invented, when books became cheap or cheaper, when the printing press was invented. The monks, the Christian monks, said, this is going to destroy society because now people are going to be able to read the Bible by themselves instead of having to talk to us. And so they're gonna believe crazy things. And in fact, they did. That created a Protestant movement in Europe, right? That was created by the availability of the printing press. Because people could read the Bible now, and so they didn't need to talk to priests anymore, and they figured out maybe there is another way to interpret religious text, right? That caused 200 years of religious conflicts in Europe. So in a way, it did destroy society, but nobody would say that the invention of the printing press was a bad thing. And then a couple hundred years later, it also allowed the dissemination of the Enlightenment and progress of some society towards freedom and democracy and stuff like that, right? Creation of the United States of America, among other things, the French Revolution. So every technology, particularly communication technology, will have good sides or bad sides. And the role of society as a whole is to maximize the good sides and minimize the bad sides. But it happens.
Yeah, I think that's the very last question, maybe.
Oh, we've got a little philosophical here. So
you've talked a lot about how self-supervised learning is the future of machine learning, but mainly the applications are mostly about videos or images or texts. What's the main, the next big step of self-supervised learning in terms of industry or other industries?
Well, a lot of people are working on sort of multimodal things. So basically models so a main limitation, and again, this is something I'll talk about tomorrow, but the main limitation of large language models and NLP system is that they're not grounded in reality. So if you describe to them a very simple situation, and you ask them a very simple question that any child can answer, they will answer it wrong because they don't have any idea of underlying reality. So let me take an example. If I describe the following situation where I hold a piece of paper between my two hands, and I tell you I'm going to take away my left hand, right? You can predict what's going to happen, right? Anybody can predict this. Even a less than 1-year-old child can predict this. Okay. So any animal can predict this. ChatGPT can. It will predict that something will drop, but it actually predicts the other way around. It predicts when you type it in a particular way, it will tell you that the paper will fall in the direction of the hand that you removed, which is completely nonsensical. And it's because it has no notion of the underlying reality of the physical world, which is one of the things I call common sense. So the big challenge for the next decade, maybe one of you will solve this, is how do we get machines to learn how the world works like humans, like animals, by observation and interaction, acquires all this background knowledge about how the world works, constructs some common sense, and then language is kind of a thin layer on top of that. And currently, NLP system and LLMs have a very superficial understanding of the world because they have no idea of the underlying physical world. So a big challenge is multimodal systems that can learn from video, but learn how the world works, and then build language on top of this to describe what happens.
Okay, thank you very much. I think that we have to close now. Thanks again for your nice talk.
Thank you.
So we have 15 minutes of break now. I don't know where. Maybe Mohamed will say. Yeah. Dans le hall.